Hey guys, today we're going to learn about a new tool called a velocity time graph, also known as a VT graph. It's kind of like a DT graph, which is the one we're seeing here, but its purpose is a little bit different. So let's refresh our memory of the story of Paco the squirrel, and let's tell it using a DT graph like we did in the previous video. Then we'll tell the same story using a VT graph to see how it's different. So Paco the squirrel was in a field one day when he saw an acorn, so he walked towards the acorn. He paused for a moment, sniffed the air, because he's a weird squirrel, and then he remembered that he was going for the acorn, so he moved towards it again. Before he could reach it, though, an eagle flew by, which scared Paco and froze him in fear for a moment, and then he retreated back to his original starting position. He took a moment to build up his squirrely courage, and then he charged forward towards the acorn. Once he arrived there, he celebrated for a moment and ate the acorn, and then he went back to his original starting position and even, in fact, moved beyond it, to a point where we can no longer track him. So that was the story of Paco the squirrel told using a displacement time graph, or DT graph. So what is a VT graph? Well, it starts out very similar in function to a DT graph. It tracks something that's going to happen over time. So just like with our original DT graph, we're going to plot time on the x-axis of our VT graph as well. The y-axis is where things change. Instead of tracking the displacement of an object, we track instead its velocity, how fast it's moving. So velocity is measured in meters per second, and meters per second of velocity could be positive, negative, or zero. So just like before, we're going to have 0 in the middle of our y-axis, and then we'll have positive numbers above and negative numbers below. What does it mean to have a positive or negative velocity? Well, that means you're either traveling in the positive direction, which in physics usually means up and to the right. And what does a negative velocity mean? That means you're typically moving in the negative direction, so to the left or downward. So this is a VT graph. And what is a VT graph? Well, it's a graph that shows the velocity of an object at any given time. What is velocity? Velocity is basically the rate at which an object's position changes. So let's tell Paco the squirrel's story one last time, but this time using a VT graph, and let's see how it looks different. One day Paco the squirrel was in his grassy meadow when he saw the acorn across the way. He moved forward towards the acorn for a moment, then he paused and sniffed the air for a moment, then he moved forward again, then an eagle flew by and he was scared so he didn't move anywhere, then he ran backwards, then built up his squirrely courage, then charged forward at a great speed, celebrated for a moment and ate the acorn, and meanwhile did not go anywhere, and then lastly ran backwards. And then we don't know what happened after that. So here's a VT graph showing the motion of Paco the squirrel. And it looks pretty weird, mostly because the lines aren't all interconnected. And also it's made up of completely flat sections, which is usually what a simple VT graph will look like. So the regions that are higher up are regions where he was moving with greater velocity, and the regions that are lower down are regions where he either had no velocity or had a negative velocity, meaning he was moving backwards. Now this isn't actually a complete VT graph. What it's missing is lines to connect each of the sections. So when you have a bunch of skyscrapers and, I guess, sewer systems down below, you'll want to connect them with vertical lines just to show that this is one continuous motion. So this is a VT graph. And what you could do is you could look at any particular section and find out what Paco was doing based on your knowledge of how the story works. So could you look at this graph and find out where he was running backwards because he was scared of the eagle? Could you find where he was charging forward towards the acorn? Could you find where he was sitting still, sniffing the air before he ever got to the acorn? You probably could, because now this is probably the third or fourth time you're hearing this story, and you can see from the graph where he was moving fast, slow, or backwards. So let's look at how a DT graph and a VT graph can tell the same exact story even while they look very different from each other. The graph on top is showing the displacement of Paco at any given moment, which is basically where he is. And the graph on the bottom is showing his velocity at any given moment, basically how fast he's going. Those are two different sets of information, which is why the graphs look different from each other even though they're showing the same motion. Is there a way you can make these two types of graphs talk to each other? Is there a way that you could interpret one and produce the other? Could you convert one form of a graph to another if you needed to? Well, yes, you could. If you take lines, and I'm using red dotted lines here, and you kind of trace all the different moments in time, like 3 seconds, 4 seconds, 5 seconds, you can actually see as you look up and down that each section in the dt graph corresponds to a section in the vt graph. For example, the first moment in time, Paco moved 2 meters forward in a time of 1 second. So we could calculate that his velocity was 2 meters per second. Now look at the vt graph. It says in the first second he was moving 2 meters per second. So if you look at the slope on the top graph, it always seems to equal what's on the bottom graph. And in fact, that's a rule that you can use conveniently in physics to convert from one form of a graph to the other. Anytime you want to know the velocity of an object and you're looking at a dt graph, just take a calculation of the slope of the dt graph and you will be told what the velocity of the object is. So at this point, you could pause the video, and if you wanted to, you could calculate the velocity of Paco at any given point, and you'd be able to confirm whether you had calculated the slope of the top graph correctly by simply looking at the bottom graph as your answer key. So this is the moral of the story, is that the slope of a dt graph can produce the velocity of an object, and therefore you could make a vt graph pretty easily from it. Let's practice that now. We're looking at a displacement time graph, or dt graph, that shows the motion of an object. Now the first part of this graph shows that the object is moving forward. The second part of the graph shows that the object has stayed still, it's not moving anywhere. And then the last part of the graph shows backwards or reversed motion. How would you make a vt graph from this? Well, there's no numbers, so we're not going to be doing any calculations today. But the first thing I would do on the vt graph is I would draw a flat, straight line that is above the zero. And that's because I can tell that that object is moving forward at a constant velocity, because that's a nice straight line on the dt graph. So it must have some kind of positive constant velocity. The second part, I'd probably put at 0 velocity for some amount of time, because that flat section on the dt graph tells me that the object is not moving forwards or backwards, it's staying still. So that corresponds to 0 meters per second of velocity, which on the vt graph is right on the axis. And then the last section shows reversed motion, because it's going backwards. And so how would you show backwards motion on a vt graph? Well, backwards motion usually means negative velocity, so it would have to be aligned below the zero axis. Now, I intentionally made this line on the bottom farther away than the other line on the vt graph from the original part of the graph, from the first part. Why did I do that? Why is this one farther from zero than the first section was? Well, it's because I'm looking at the slopes in sections 1 and 3 of this dt graph, and I'm noticing that it's a steeper slope on part 3. A steeper slope corresponds to a greater velocity. So whether it's positive or negative, steep means really, really fast. So since it's a faster velocity at the end of this journey, I'm making sure that that velocity I'm showing, even though it's negative, I'm making sure it's a big number to show that it's a faster speed than the original speed. So that one's a little bit complicated. Here's one that's just one step, but it's complicated for a different reason. Sometimes you'll see curved graphs like this one. A dt graph that is curved shows that the speed is not staying the same, but in fact it is changing. A changing speed, meaning maybe a car where you hit the accelerator and you go faster and faster and faster, is going to make a curve shape like this, because the slope of the line represents its velocity. If the velocity changes, the slope should change as well. So how would I turn this into a VT graph? Well, I can see that at the very beginning, the graph starts out kind of flat, and by the end, the graph has a really steep slope. So I need a VT graph that also shows that the speed starts out low and then the speed ends up high. So it would look something like this. A straight increasing line on a VT graph shows that the object is accelerating. And a curved line on a DT graph also can show that the object is accelerating. It could also show deceleration too if the curve was facing the opposite direction, flattening out over time. There are all kinds of really complicated shapes of graphs that you'll probably see as time goes on, and you'll get very used to recognizing the patterns of what a certain curve or straight line or flat section means. That'll be the challenge of this upcoming unit. So I wish you luck, and I'll see you in the next video.